Good morning to all. Welcome to KIT Knowledge Series. I'm happy to note that Department of ECE of our institution has organized a webinar on planar antenna design for real-time 5G modem applications today. Thanks to the head of ECE department and all the members, in particular to Ms. Sindhumati for organizing this webinar today. With great pleasure, let me introduce the guest speakers. The first speaker is Dr. Sugadev Mani, Assistant Professor from Satyabama University, Chennai, as well as Head RF Research Wing in Wilma Communication Groups from India. He has 18 years of experience and he has completed 22 projects successfully till now. His area of interest is antenna system design and embedded system. The second speaker is Engineer Vinod Manoharan, founder and head Wilma Communication Groups from Asia and US, Future Techies from Asia, Field Science from Europe. He has totally 12 years of experience. So far, he has completed 252 projects successfully, 185 projects in Asia, 40 from US, and 27 from Europe. And his area of interest are antenna system and satellite transponder design. So on behalf of the management, staff and students of our KIT family, I extend a warm welcome to both the guest speakers. I also welcome all the participants from various institutions and organizations. And I hope this webinar will be definitely useful for those people who are really working in this area. So have a nice day, and let me hand over the session to Ms. Subita. Thank you.
Hello, everyone. So to be a successful person, you should have a heart in your business and your business in your heart. Yes, obviously, it is being true and applicable for all the steps that you take in your career. A very pleasant good morning to all the ladies and gentlemen who are present in this forum. This is me, Sumaitha Jiva, and I'm being active in the platform that enables to come out with an innovative ideas. Yeah, I'm working in Wilma Comms and the creative teams in India division. So getting into my point, it is not that much easy to build an organization. Of course, it takes hours, months, years, and sometimes even a decade too. So, but today I wonder how an organization can bloom like anything for the past 14 years till date. And we are being successful in all the products and research development areas, as well as web development, application development, server designing and maintenance. And we are training n number of students from various candidates, and we strive a lot in order to organize various workshops, seminars, national and international conferences, and so on. So we are having three concerns. So let me tell you what is our focus and our works related to it. The very first one is Wilma Comms, so which is nothing but wireless LAN make associate. Okay, we are working on new taste, which is depending upon the recent trends in the technology that is running right now. So we are focusing in 3 countries. The very first one is US. We are being a channel partner with Toshiba in the field of antenna designing, research area. So we are being working with Toshiba in US, and this is all about Wilma Comms. And the next thing is Future Techies. Future Techies is actually working in Asian countries, both WZ and the Future Techies. We are working in Asian countries now. So, and what is the role of this Future Techies is we are moving a step ahead and marching towards the future technology by gaining and assisting all the young minds of the nation. So we are going behind them. So we are collecting the ideas and we are transforming all their imagination and we are implementing them in order to broadcast their talents. So this is what is the role of Future Techies. And the very next one is Field Science. So this is actually the dignity which we have received from European country, as we have done n number of communication based projects over there. So we have concentrating on 2 things. One is microwave based project, another one is communication based projects. So these are the 2 things that we are working at the present. And we have collaterals with the DIT universities, which is known as actually the Temple of RF. So we are having collaterals with them. So when you take Wilmer Comms, we are having partnership with around many countries, no? So in the field of research and development, and we also have collaterals with few of the universities and companies too. So we have successfully completed more than 200 plus projects in our concern. So we are looking for many such things in the future too. And apart from this, we have our own fabrication and supporting testing based unit in our concern. And we also have now from yesterday onwards, we are having tie up with GAT Light, so which is actually known as the world's number one leading electrical manufacturing companies. When you take in Asian countries, along with GT Light, we are also having the tie-ups. We are the authorized channel partner for Navitel or telecom corporations, which where their role is to make the communication-based devices. So this is what is their role. So the next thing is we have successfully completed more projects. Let me enumerate a few of them. The very first one is 5G smart cell antennas, then radars, for balloon satellite, then army purpose, then microwave system measurement equipment. So these are a few of the successful projects that we have done so far. So to be simple, we are working in a way in order to solve all the communication-based problems in the recent trends with the help of wireless technology and as well as the software solution. So this is what is a role there. And the very next thing is, coming to the point, we are bringing all our efforts together in order to bring a complete engineering solution to the students and as well as to the society. So this is what is our motto and running behind. So coming to the satellite communication design based projects, we have worked and successfully completed 2 communication based and 1 agri based satellite projects based on the students education systems. So at present we are working in 2 to 3 communication based satellite projects also. So that will, you can see that in soon in future. Then the next thing is all about the web development and application developments. In India, we are focusing in order to provide a complete farmer solution under Digital India scheme. And we are designing the website with the help of blockchaining in order to ensure the security related issues. Hope it will be really useful and it will definitely provide a complete solution for farmers. And the main motto of this project is like we want to avoid the black marketing completely, and the very next thing is to benefit the small scale farmers too. So that is what is needed at the present situation also. So apart from this, let me now put forth few of the applications that we have developed till now. The very first one is UPMC, which is known as Union Public Medical Council, which is at US. Another one is ASL, which is known as Adric Solutions Limited, which is at US and as well as Italy. The next thing is KISAT, so which includes multiple elements like food products, groceries, and you can have like many things in that. So what is the thing is we are putting a complete solution again to all the UAEs, which is known as United Arab Emirates, for their online sales. So this is what is a role. And at present, if you see, we are working in few projects apart from the satellite works and all, like underwater antenna communication related antenna research works is going on there. And the next thing is ham identifier for security purpose with the help of blockchaining concept and advanced future technology based high speed modems. So of course, I still believe and we are all working for that to complete it successfully. The next thing is we are being specialized in providing all the medical emergency equipments with the help of frequency based antenna thing. So we are working on it, and successfully we have also done few of the things, like you can see, like abdomen scanner, bone scanner, cardiac analyzer, intestine scanner. So all these things are the thing we have successfully completed and doing researches till now in the field of biomedicals. So you can see from the year of 2007 till now, we have successfully completed, as I already said, more than 200 plus project. You can see a linear growth in the performance till date. And we have our clients and research collaterals with various institutions and colleges till date. And at last, don't you feel like we are doing something really great that is tough to move with? Yes, we are nailing something epic till date and even forever. So let me wind up my presentation by conveying two things. So first of all, let me thank Engineer Vinod Manoharan sir, COH, co-founder of WC Groups, who has given me such a wonderful opportunity over here. And I also like to welcome you all for the one-day webinar on the 5G related antenna works. So all the best. Go ahead, and it's my duty to hand over the session to Dr. Sugadev, who acts as the external research advisor of WC Groups. So thank you once again. Have a great day ahead.
Thank you, Sumedha. Good morning, Mananda. I am Dr. Sugadev, working as assistant professor at Satyavama Institute of Science and Technology. And I'm also engaged in the consultancy of real-time projects along with Wilma Communication. I should thank Engineer Vinod for giving an opportunity to learn practical things in antenna design, testing, and all that. Because from academic background, it's tough to go ahead with research projects which can be really deployed in real-time applications. So an exposure and contact with Wilma Communication has broadened the window of practical knowledge, and it helps myself and my students and the other research faculties to enhance the practical skill in antenna and other RF circuit design. Actually. And also, I thank the organizer for giving us an opportunity to present this one-day webinar on the antenna design for specific 5G application. Okay, so to begin with, just see what is 5G and what are its services and goals. And it has not been fully developed and deployed in all the countries. Right, it's in the beginning stage, and the standards vary from country to country. Still, it is not yet globalized. Actually, there's a big dilemma in choosing the frequency band and the technology behind each device. Still, there is a dilemma going on, and so it has not been a complete global standard yet. And with the literature survey and what is being used in other countries, we'll see what about 5G, the technology behind it, and what are its intentions, and what are the frequency range that are proposed to be allotted for 5G. And we'll proceed with a small application. We'll take up a small application in 5G area and start learning how to design the antenna with a electromagnetic software tool. So, okay. Okay. So the presentation mainly focus on a microstrip antenna designed for a sub 6 GHz 5G application. Okay. So what are the services that could be provided by a 5G infrastructure when it comes to play in full form, actually? So there are three goals for the 5G services, and this encompasses almost all the uh, things we use in our day-to-day life. Nothing is left out, actually. So the ultimate motive of 5G is get connected to anything, everything, and everywhere. That's a motive, actually. So this applications can be broadly classified into three. One is the enhanced mobile broadband. Actually, we have a mobile service and a 4G standard, and the motive of 5G service is to enhance that. A simple example is now the maximum speed you can get with a 4G, that the peak speed we used to say, it's 1 gigabits, right? But the goal of 5G network is to achieve tens of gigabits per second, actually, in the mobile broadband network. And then it should also connect smart to all things in your home, office. So we could say it is a small home or small building where we talk about IoT, right? So 5G also defines standards for Internet of Things actually, and the protocol behind the connectivity of all the things that would make up the IoT applications. Then it is going to be the backbone in smart city as well actually. Then the next one is massive mission type communication. So you take automobiles now; they don't have a network actually. So in the future, when 5G comes to play in full swing, so all the vehicles will get interconnected with one another. And if you see some cars going on the road, so every car will be a mobile node. Every car will be a mobile node, and they themselves will talk among one another, and they could share information about the traffic, the road condition, and so on actually. So the goal is to connect all the missions. It could be cars, vehicles, and anything else actually. The third, so we say it is massive mission type communication. All the missions are estimated to get connected and communicate among themselves. So they can prevent accident, they can serve the people with comfort, and also they can provide emergency services as well. And the third one is multimedia communication. So now you could see we have a live stream of video conferences going on in HD. And when 5G comes into play, then we could have ultra HD live conference. That would be possible because the goal in 5G standard is to live stream ultra HD. Even a live conference in ultra HD would be possible. 3D videos and high quality voice, and then making use of the cloud infrastructure actually. So yeah, destination node need not have a big resource, and the cloud will provide the resource in the background. And then augmented reality, automation of industries, then mission critical application, e-health particularly, it is going to play a great role in e-health as well. And then self-driving car. So you could see the motive of 5G services is enhancing or invading in all aspects of life, and nothing is left out. So they want to get connect everything what we see around and use in our day-to-day life. And the motive is ultra reliable actually. So if you are sending millions of packets, you could expect some just one or two packets lost. So that's ultra reliable. So whatever you transmit, that will reach the destination without any loss of packets. So information will not be lost. And then low latency. So latency is the delay in the communication. If you transmit something, so definitely it will take some time to reach the destination. The goal of 5G network and circuit design is to reduce this latency in communication actually. So they have fixed the latency to be 1 millisecond, and they plan to bring down the latency to 1 millisecond as well. So this is the focus of 5G services, and now all people are researching on the infrastructure, say the transmitting side, the antennas, and other software development, because it will involve a lot of software in the background because it makes use of the cloud and other resources. So all this are parallelly going on, and whatever they have completed, and it comes into application actually. So still we have a very good scope in research on the 5G infrastructure. So you can take any domain which you are interested and carry on with your research actually. Okay, so, and this slide gives the performance metrics that is expected from the 5G services when it is rolled out actually. So massive Internet of Things, so connect everything. So you could see millions, billions of nodes that will now get connected to the internet, and the network should be able to withstand that capacity actually. So that's a massive Internet of Things where millions of even billions of devices would get connected together. So the network should be able to handle that much number of nodes actually. And ultra low energy, so the power consumption should be reduced as well. So 5G devices are expected to consume very less power when compared to 4G and other standards. And then deep coverage, so they want to take 5G to each and every nook and corner of the region, so that everyone will have a reach on the 5G services actually. Then ultra low complexity, they want to bring down the complexity as well. So I could say 5G would be a more or less fully adaptive system, right? So based on the requirement, it could go into a higher complexity. When it is coming down to IoT, the complexity will be very less, where it is required to transmit data at a very low rate, right? So it will be a fully adaptive system actually. So the maximum could go on in tens of gigabits, and the minimum could come on bits per second actually. So it could sense the environment, and it should be able to adapt itself according to the network condition, traffic condition, and so on actually. So extreme capacity, we have discussed, it must be able to handle the data coming from billions of nodes. So they expect 10 terabits per second. It should be able to handle that much capacity of data actually. And data rates, they are trying to, in cellular communication, their goal is to come down to 10 gigabits per second, whereas in wired or optical network, so they're planning to go ahead with terabits, even 1 terabits per second or even more. That one. Okay. Strong security. So security aspect as well. So it should be immune to hacking from the other people actually. Ultra low latency, as low as 1 millisecond, and then extreme user mobility. So the user can be in mobile. That's we are experiencing 4G. So then what's in 5G? You could say, for example, you could travel in an aeroplane and then still you have mobile connectivity. So that's extreme mobility. Even you can travel too fast, but still communication will go in a sustained manner actually. Okay. So coming down to this frequency allocation for 5G, this is still in a, how to say, ambiguous state actually. So all the countries have not come to a specific conclusion on what frequency to be used or allotted for different 5G services. So it varies from region to region, and people are rolling out 5G applications with whatever they have standardized actually. So the first frequency range that could be used in your mobile phone could be the sub 6 gigahertz range. So people used to say 5G service will use millimeter wave service that is beyond 20 gigahertz, but that's the case. But they also allocate frequencies below 6 gigahertz, sub 6 gigahertz, and even megahertz. For example, massive IoT devices where the data rate will be very less, where they want to cover longer distance. Even they are exploring the use of ultra high frequency band, UHF band also actually. So in sub-gigahertz range, actually for the mobile communication, they have almost agreed upon this 3.3 to 4.2 gigahertz, and within that, each country could fix different center frequency. For example, the Korean countries uses 3.5 gigahertz for that mobile cellular band, and they also support millimeter wave spectrum. Suppose if you want to access download data at a high rate, then your device should change the spectrum to millimeter wave, and then it could work fast actually. So as I told earlier, the 5G system will be adaptive. Even your mobile phone will be adaptive, and it will be able to operate in the millimeter wave band as well as the sub 6 gigahertz band actually. So the next frequency range that is allotted for high bandwidth, high speed application is a millimeter wave. Above 20 gigahertz, generally we say it is millimeter wave communication. So 24 gigahertz, they are greater than 24 gigahertz, they identified. And that particular, in US, people started using 28 gigahertz, and AT&T started using 29 gigahertz. So the limit for 5G is up to 300. So that's a maximum range of the microwave band we have seen in our textbook, like 300 gigahertz. So researchers are exploring to use up to that 400 gigahertz, even 6600. So research is going on, but commercially they have come up to this 28, 39 gigahertz for commercial rollout of high-speed Wi-Fi application, broadband, mobile, and particularly for mobile voice communication at and a low data rate, that is 1 gigabit per second. People will be restricted to this 3.5 gigahertz band actually. Okay. So these are the three coverage frequency bands that have been allotted for 5G services. As of now, whatever services you hear of, they use one of this frequency band actually. But still, they are exploring up to 300 gigahertz to achieve the maximum speed. Okay. Right. So as I told earlier, the focus of our webinar today is on the antenna design for any of these frequencies actually. So fundamentally, if you learn to design for any particular frequency, you can design whatever frequency given to us. And the electromagnetic tool what we are going to discuss and see today, it can be used to simulate up to 300 gigahertz. So there is no problem in that. You can work up to 300, even beyond that it would support. And then you can, if you are satisfied with the simulation results, you can go ahead with fabrication as well actually. Okay. So I have taken microwave antennas because, as I said, the sub 6 gigahertz band, it's mentioned some modem for a modem application that also falls in the 3.5 gigahertz band actually. So I'll take that frequency and I'll show you how to design and analyze a antenna, microstrip antenna here. So since mostly we use the microwave frequency for the millimeter wave communication, that is the 5G communication. So the what are the type of antennas that are good for this 5G application, if you could ask, then probably it could be the microstrip antenna because it will be more compact and easily you can increase the gain and you can build arrays and you can go ahead with phased arrays where you can do beam farming. That is, you can direct the radiated beam in a specific direction or the direction of interest. So all this would be possible very easily with the microstrip antenna structure actually. So for high power application, of course, we can go for that parabolic dish antenna and radars and all. They use that parabolic dish and other things. But for compact and portable wireless devices, microstrip antennas are going to play their role in the coming years as well. Actually, previously, past 5 to 10 years, almost they have invaded all wireless devices, and they are going to continue their stand on another 3 to 5 years definitely in all the wireless devices. The reason is it is because it's a planar device. It's very convenient to fabricate in the PCB itself. Along with the PCB, you can simply etch a patch and fabricate your device. So because of that convenience, microstrip antennas are greatly they're preferred for the compact and wireless applications. Okay. So I'll go ahead with the fundamental of a microstrip antenna actually. So microstrip is basically a transmission line which will have a ground conductor and a dielectric layer above that, and above that you have a another conductive layer that will act as the positive terminal. So a dielectric is sandwiched between two conductive layers actually. So that structure is generally called as a microstrip line, and it has been a alternate transmission line for waveguides. You all know at microwave frequency we used waveguides and that are not convenient for compact devices. They are larger in size, they are not flexible, and so as an alternate for low power microwave applications, people develop the microstrip transmission line so that they can conveniently make microwave circuits using that structure actually, because the structure is similar to the PCB what we have seen. A PCB will have a ground layer at the bottom, then a dielectric layer above that, and above that another copper layer they can put. It becomes a microstrip structure, right? So along with the PCB itself, you'll be able to make that microstrip line and even connect antennas and all that. Okay, so then later on, people started designing antennas with the same microstrip structure. If you look at this picture, you could see a microstrip antenna consists of a ground plane, which is a metal layer at the bottom, and then above that you have a dielectric material, and then above that again you have a metallic layer, that's a conducting layer, a metal patch we used to say. Of different shape you can use. It could be square, rectangle, circular, triangle, anything. And then we slightly extend the copper patch on the top to the edge of the structure so that you'll be able to connect the signal to it actually. Okay? And this is the fundamental structure of a microstrip antenna actually. Okay. So this structure closely resembles a microstrip transmission line actually. So it is called as microstrip antenna. Okay. So what are the patches that we could be able to use on the top conducting layers? As I said, it could be rectangular, square, circular, annular ring, elliptical, triangular, monopole, and so on, anything, any shape, whatever shape you decide to use, you can make it and try actually. Okay? Right. And this is the feeding techniques actually. So you are making that structure, ground layer, that substrate, a dielectric substrate, and above that you are making a cover patch. Then how do we connect signal to that? That's called the feeding technique. How to connect our signal that has to be radiated to the design patch antenna. So the most simple one is the line feed. Actually, you can simply extend the copper patch or the metal patch to the edge of the structure as shown in figure A, and then at the edge you could use your connector, SMA connector, and then connect your source to it. That's one thing. But the impedance matching, this is the rectangular patch will have some impedance, and the source will have 50 ohms. And simply using a straight rectangular feed line of very small thickness will not provide a impedance match, and there could be losses. So the antenna may not perform well when we go with this. So what the people do is they'll try changing the position. The feed may not be at the center. It could be on the top, just slightly above the center, or it could be below the center. And we can find out the exact matching point, and then we can fix it. That's one simple option. The other most popular one is that inset feed actually. So we can just make a cut where the feed line and the patch meet actually. This is called the inset, a small cut at the meeting point of the feeding element and the patch actually. So this length and width of the cut you make here will decide the uh, amount of matching actually, impedance matching. We can do that. So this one way, and then we can also use a quarter wave transformer that's more simple than this inset feed, which I'll be demonstrating in my design actually. That's also possible. So some we have to take care actually. If you just simply use a straight line feed, you can't achieve perfect matching. Actually, there could be losses in the antenna performance. So some sort of a technique should be used to reduce the losses. That means to improve the impedance matching between the patch element and the source actually. Okay? The older feeding type is the coaxial probe one, but nowadays no device will have this coaxial cable. It is obsolete. No people use coaxial cable for connecting the signal to the patch actually. It is an obsolete thing actually. So we have to concentrate on the line feed and make some techniques to match the element to that. Then the other one is proximity coupled, where the feed line is not directly connected to the patch actually. So it is just in proximity, somewhere near to the patch. And this structure requires two different substrate, one and two, to sandwich the feed line. And so this is also very difficult to fabricate actually. So this could minimize loss, and it could be preferred in some applications, but again, in fabrication point of view, it is very difficult, and it could increase the cost of your device actually. So you can go with the basic structure what we have seen in this. Okay. So this is just an example of several microstrip antennas that has been designed and how we fix the connector. So you could see the small antenna with a single patch and the feed line, and it is connected to the SMA connector. Okay. Then the left side, what you see is an array actually. So it's very convenient to design array antenna with microstrip. Simply you can extend or duplicate the patches you design on a larger surface, make as many you want, and then connect the feeding signal in some popular pattern. And then you could get a microstrip array which will have a higher gain and more directivity actually. And this could be a required design for 5G mobile applications or the 5G base station stills. It could be using an array of microstrip antennas. So this coming to the patch shapes actually. So what I have shown previously is they have used a standard rectangular circular, and there is no limitation on the shape of the conducting patch you put on the top. That's a radiating layer we used to say. So you can try different shapes on the conducting layer, even as well as ground layer. It may not be a fully copper clad ground layer. You can introduce some defect in that. So that means you can make some etching in the ground plane or on the top radiating plane, and you can have different shapes as you wish, and you can analyze actually. So if you could get better performance with your unique shape. That's well and good. So people, why do they go with these different shapes? Is that to achieve higher gain, to achieve multi-band performance. So normally a rectangular antenna will work for a single frequency, whereas if you try some innovations in it, you can make a single antenna work for different frequencies, 2 frequency, 3 frequency, and you can minimize the losses in that. You can increase the gain, polarization you could change. So all this are possible by simply playing around the shape of the patch and the dimension of that actually. Okay. So it is quite easier when you become familiar with the electromagnetic tool. Any tool you can use actually. So this slide shows some of the applications. It is quite convenient for wearable application. You can make with some flexible substrate, then you can use it for wearable application. Mobile phones, all mobile phones will have a microstrip antenna, but they will have a unique shape actually that the company people would not reveal that. All your Wi-Fi modems, Wi-Fi modules you are used, RF modules, Bluetooth modules, and all this you could see a small patch element that's acting as the antenna actually. Okay. So what is the scope of microstrip antenna? It is very compact and very easy to design patches. Beam forming is possible. That means you'll be able to steer the beam in the required direction by employing phase shifters. And you can employ digital signal processing techniques for the phase shifters, and you can go ahead in building the smart antennas. So different structures of patch shapes can be studied to achieve multi-band operation, optimized antenna performance, and so on. There's no limit in that actually. Okay. So these equations are from the Balanis book actually, and they have been defined for a standard rectangular patch antenna. So when you start with, you practice designing a standard rectangular antenna, and then you can make changes in the shape of it. So fundamentally, you can design a rectangular or a circular antenna for which the design equations are available, and then you achieve the desired resonant frequency, and then you can make changes in that actually. So okay, I'll tell you if you are a little bit stuck with the large equations. I'll tell you how easily you can design antenna with the online calculators that are available. Actually, I'm not going to use this complex equation. I'll simply use some online antenna calculators available for Microstrip, and I got the dimension. Okay, so now we'll proceed with the design of 3.5 GHz patch and actually. So whatever it is 4G, 5G, 3G, or whatever it is, as far as antenna design is concerned, we have to see only what is the frequency range for which it has to operate. Then we have to see what is the bandwidth required, because that decides the data rate of your transceivers actually. So as far as the antenna engineer is concerned, we see what is the frequency range for which they need the application, what's the limitation, the dimension, what should be the size, maximum size within which we should design the antenna, and then how much power we are going to transmit. Generally for low power, microstrip is well and good till 1 watt. There's no problem with microstrip patch antennas actually. And then the gain, how much gain is required, type of radiation pattern. This is what we are concerned, and we not to bother about what is the technology, 5G or 4G, whatever it is. So we'll consider a microstrip antenna that has to work at 3.5 GHz, and let us see how to design and analyze that antenna. Okay. So once again, I'm showing the structure of the microstrip antenna because this is what we are going to design. And what difference you see here, instead of that insert feed, let us try using a quarter wave transformer. This just a stretch of microstrip line can act as a quarter wave transformer, and this could provide impedance matching in the antenna actually. Other than that, it remains the same. Okay, and then the other important factor is having decided what frequency you want, what is the bandwidth required. You have to decide on what is the substrate material you are going to use, what is the dielectric material you are going to use, right? So that you cannot choose anything as you wish, because you should see what is available in the market. Because if you want go to fabrication, you have to buy it and make it, right? So you have to see what is available in the market, which is cheaper, all this. So the most popular type of substrate that are available for Microstrip, are commonly used for Microstrip, and the most popular one is RT Duride and Erlon, but these are all a little bit costly actually. So now people started using FR4, which is the common PCB material used for designing electronic boards. And now most of the designs, if you look in the journal articles, they started making with the FR4 itself actually. So we choose the same FR4 substrate because it is much cheaper, and within 700 800 you'll be able to fabricate your antenna after you have successfully designed actually. Okay, so for this example, I'm going to demonstrate with the FR4 substrate, because you see the size 100 centimeter, sorry, 100 mm, 10 centimeter cross 7.5 centimeter, costs around 99, and thickness of the substrate is 1.5 mm. It's available 1.5 mm, 1.6, 0.8. So that's also very important, because when you design the antenna, the thickness of the dielectric is going to decide the frequency, right? So we can't randomly choose any height of the substrate, because you should see what is the thickness of the substrate or the PCB material that are available in the market. So after making a survey, then you can fix it. The common FR4 substrate, PCB substrate, is having a thickness of 1.5, and 1.6 is also available. 0.8 is available, 0.4 is available. So we should fix this first, what material and what thickness we are going to use. This just for example I have shown. As you see, it is 99. If you go for RT Duride for the same size, it could be 1,500 or 2,000, and if you go for Arlon, it will be still costlier than that. Maybe you may get some better performance with those materials actually. Okay. So as I said, I'm not going to calculate anything, and I have used the Microstrip patch and a calculator available online in the website EM Talk. Anything, many websites have posted this. So here what you have to enter, right? So what is the dielectric constant? The formula, it's there. You not to worry about that. So just mention what substrate material you are using here. So we have chosen FR4, right? FR4, the dielectric constant is 4.4. And the height, what I have chosen, the board, what we have commonly used is 1.6 actually. That's the material we have got. Okay. This is the thing about the substrate. Okay. And then what frequency I need, just we have to enter. We have to design for 3.5 GHz. So when you enter these things, it will calculate using this formula, the width and length of the patch actually. So the width and length of the patch will be calculated by this tool, which is using this equations in the back end. You have a code behind this using this equation to give this values. Okay. So we got L as 19.987 mm. You can round it off 0.988, and the width of the patch 26.08 actually. So the design is over. I just gave, and it also mentions what is the input impedance at the edge. So at the edge of the square patch, its impedance would be 243, but the source impedance at the edge, what you are going to connect, would be 50 ohms or 70 ohms normally. So obviously there will be impedance mismatch, and we'll see what is the impact of that. Okay. And how for that purpose only we are using that quarter wavelength transformer what I shown here, and this will provide the impedance matching. Okay, right. So we got the length and width for this. Thickness already we know. What material we are going to use, we are aware of that, because we have chosen FR4 here. And then what is required is what is the length and width of the substrate, because you are going to make the patch over the substrate, right? So for that, no calculators are required. So you should, the gap between the patch and the substrate edge, no, it should be lambda by 4. That's all. So you should leave a space of, or you should add a space of lambda by 4 on the left side of the patch, right side of the patch, and on the top side of the patch. That's all. So here the length may vary depending upon the impedance you require actually. So this may be lambda by 4, or even could be longer, or even could be shorter. So the length on the feed line side may not be exactly lambda by 4, and it could be longer than that, or it could be smaller, so as to achieve matching. But on the top left and bottom sides of the patch, you can have a length of lambda by 4. So just if you want to find out the width of the substrate, so just add lambda by 4 this side and lambda by 4 on the left and right side to the width actually. So W plus lambda by 4 plus lambda by 4, that will be the width of the substrate. And then length of the substrate would be this L length of the patch plus lambda by 4. And to make it simple, I have chosen lambda by 4 length even in the feed line domain actually, but slightly it should be greater to achieve better matching actually. So I just L plus lambda by 4 plus lambda by 4, and that gives the length and width of the substrate actually. That's all. So we got all the dimensions of the antenna, and now we have to design it. We have to design with the electromagnetic tool and study whether it will exactly work for that. So having entered this frequency, dielectric constant, dielectric height, if you enter synthesis, if you select the tab synthesis, you'll get the length and width automatically. Okay, and then this is to find out the feed line. Actually, it's a microstrip line calculator because the feed line is a simple microstrip line, right? So what should be the thickness of this microstrip line? I want to, we can design this actually for proper, randomly you can use it, but if you design, you'll get somewhat better performance. So what should be the width of this microstrip line? Length, of course, we have to change to achieve, we can optimize the length, but the width should be calculated according to this guideline. So in the same website, EM Talk, you have a link for microstrip line calculator. So here also, this is for the feed line I'm talking, not about the antenna patch. It is for the feed line with this one. So this is a feed line, small extension of the patch you have. So what should be the width we should use? Okay. So for this also I used a tool. I entered dielectric constant, dielectric height, and then the frequency of interest, and then what is the impedance required. I need 50 ohms. So if you give synthesis, it will give the length and width of the feed line. Actually, it is giving 2.98, and I have kept the length of the feed line as 21.42. So actually, this 21.42 is the lambda by 4 value actually for the frequency of 3.5 gigahertz. Lambda by 4 becomes this 21.42. Okay. So using this, we can also roughly get, but it's not exact, roughly get the dimension of this. Then we can optimize to achieve required performance. So, okay. So here you could see the summary of all the dimensional parameters of the microstrip antenna to get a frequency range of 3.5 gigahertz. Okay. So resonant frequency, we choose it for according to the application. Material, we have to choose FR4, so it is 4.4. And FR4 different categories are there. If you want a higher dielectric constant 5.1, it's available. You could see the classification in the FR4 material and choose the right one. 4.4 is more common and cheapest one. And length of the patch we calculated for 3.5 gigahertz. Width, you got it. Then length of the substrate, this we have obtained by adding that lambda by 4 on this right side, left side, and top of the patch. So we got the substrate length as well as substrate width actually, right? So I hope it's clear. The substrate length and width is obtained by adding lambda by 4 on to the length of the patch on top as well as the bottom. That's what we have done. And similarly, width is obtained by adding lambda by 4 to the right and left of the substrate actually. So we got this time. It's fairly around 6 centimeters. Your antenna size would be along with the substrate. It is around 6.8 centimeter actually. Okay. So feed line width, we have used this microstrip line calculator, and we got it around 2.98 mm to get an impedance of 50 ohms. And then feed line length, it is 21. I have used lambda by 4 actually, but to be more precise, it could be slightly vary actually. But to make it simple, I had simply taken a length of lambda by 4, 21.42 mm actually. Right. We're now, before introducing to the software, I just want to make sure any questions if you have, you can please call. Before going to the software, if you have any doubt, you can ask. Okay, may I proceed? Okay. Where we got this LN W equation, I said the standard book for microstrip antenna design is Balanis. design and analysis of antennas by Belanis. So in that one chapter is dedicated to microstrip antenna. So you could find the complete design equations for a rectangular patch, a circular patch for both the designs. So almost all the design is derived, not derived. We just take the equations what is published in that book actually. Till now, that's a standard equations which you can rely upon. Actually, even all the tools, online tools available, it's based on those equations only. So they have put the equation for two models, transmission line model and other model actually. So this is the one based on transmission line model, which is more popular and it work accurately. Right. Then next thing is we have designed it. Now we have to simulate. We have to create the design and analyze whether it works at the design frequency or not. Actually, how we have taken dielectric constant and dielectric height. So actually, if you look at the equation, the resonant frequency of the microstrip antenna depends upon the length and width of the patch as well as the height of the dielectric substrate and the dielectric constant of the material, right? So obviously you are making the antenna with a dielectric material. So above that only you are going to make a patch of copper on that, right? So what material you are going to use for fabricating your antenna? So based that one, that's going to decide what is the dielectric constant and dielectric height. As I said, the PCBs are not available for any desired height actually. They make only for standard height. 1.6 is more standard, then 0.8 it's available, 1.2 it's available. We have to find. If I'm going to use FR4 because it is cheaper, then I should explore in the websites or in the shops what thickness they make actually and what is their dielectric constant. So that decides it, right? What substrate material you are going to use and what thickness that's available, right? That you are going to buy it obviously, right? So that based on that only we choose this dielectric constant and dielectric height actually. Okay. So you can simulate with any height. There's no issue in that. But when you end up with fabrication, then if that height is not available, that dielectric constant is not available, you can make a dielectric material on your. You can make it, but you have to spend a lot of money for that, right? So it's you can avoid that at the beginning itself by choosing the material that is available and thickness as well actually, that material as well as the standard thickness that is available. So which one is a good shape? I told to begin with, all people go with the rectangular shape actually. It's quite easier. You can design a rectangular patch antenna for any frequency. But if you try your own shape, I have shown some example. Some people who have used the shape of E, some people just a straight line, not even a rectangular one. You can even make a shape of dipole, anything you can try on that. And obviously it will make a difference in the performance actually. So for standard design, rectangular is okay. That's well and good actually. You can go ahead with rectangular. And then if you want to optimize, you can go on with you can just make some changes in the standard shape you have. When you just make edges, cut the edges, you'll get circularly polarized wave. You put a slot in the rectangular patch, you get multi-band operation. So all this we could try it actually. So that's a research we have to do. Okay, how to select ports, sir? In the software simulation, we'll discuss that. Mostly for microstrip antenna, lumped port would be fine actually. So you can select a lumped port when you are simulating the design in the software. Okay, right now I'm going to use the ANSYS electromagnetic desktop software because we are used to that actually, and it is widely used in industry as well. There are other popular tools, Antenna, Magus, FICO, CST Studio, all are popular, but I did all my research, and in our university, they have created a facility on this ANSYS HFSS actually, and even they have a network analyzer for testing. So we are used to in this software HFSS, but the same design can be made in any software. That's not a problem. So what is available with you, you can try it out. Okay. So I'll now open the software and tell you how to design it. Of course, this video will be recorded, and then if you want to learn by downloading the evaluation version, student version from the website, you can try it actually. Or if it is available in your institution, you can try ahead. Okay. So I'll open the ANSYS electromagnetic tool. So its name is ANSYS Electronic Desktop. That's a name they are given from 2019 onwards, not ANSYS HFS. It's included in that actually. It's a complete package of 4 or 5 tools. Okay, this is actually a 3D tool. If you look at the environment, it is a AutoCAD environment. So you have to just create the structure. So, but when we studied the subject antenna and wave propagation, right from the first page to the end, we see all mathematics actually. That is required to analyze the field. What will be the field component actually? So we need that mathematical stuff. But now those mathematical stuff are done in the software actually. They have their own solver, FEM solvers, and they will do the computation. And what is our job now? It is restricted to the creation of the structure. So whatever structure it's a 3D tool actually. So you can create any 3D structure. It could be a planar structure. It could be a 3D antenna like your dish antenna, dipole, horn antenna, anything, any micro component you can create in that. You create the structure, exit it, and see what's the return loss, VSWR, radiation pattern, all that. And that's no need to worry about the mathematical thing. Later on, you gradually, parallelly, you learn the mathematics, and then you can you'll be able to optimize your antenna. Okay, so if you look at this, it's just a 3D environment where we have to create the structure actually. Okay, right. So, and the left side is the project manager where we see what are the current project that's open actually. And then this is the coordinate system, and this window will list out all the objects we create. What are the objects we create here that will be listed in this, right? And it has all libraries. You could see the various shapes. Any shape you want, simply you pick up that library and then you can draw it here. So the PPT also I have put the procedure. I'll just show what I'm going to do and then enter that. So first I'll start with creating the substrate. So I'll create the substrate, and you know the substrate length is 62.828 mm and 60 length. Width is 68 and length is around 62 point, and its thickness is it's not mentioned, but we know it is 1.6 actually because we have chosen FR4 with size 1.6. So thickness of the substrate is going to be 1.6, right? So when you create a 3D structure, definitely we have to draw it with respect to some coordinate. So for this structure, a rectangular coordinate would be fine. So we are going to draw the structure with this rectangular coordinate. So I keep the origin at 0, 0, 0. So from with respect to that, I'm going to draw. So the X is the red line and Y is the blue line and Z is the height actually. So I'm going to start from 0, 0, 0, and first I'm drawing the substrate. As you know, the length would be 60. You can check here. The length would be 62 and width would be 68. Okay. So it is a box actually. So it has some finite thickness. So we have to select a box, draw a box. I'm going to draw a box. You not to draw at the right position. You draw somewhere in the workspace. Then you can enter the dimension for that box, and then it will go and fit into that exact position actually. So I'm not drawing here with respect to the coordinate. Just randomly I draw a box here. Okay. So when you create a box in the workspace, you could see the object is created in this model window actually. And initially it is vacuum material. We have to change it. So double click on that. You can right click, properties. You can edit the material, or the other ways you simply click on the box. You give some name actually. So first we are going to create the substrate, right? It's not vacuum. I have to select the material. So I'm just editing it to select the material. You have a list of materials, various materials that could be used. Rogers is the RT Durad, what I told is the Rogers material. Then you also have Orlon in this. Any material you can try it out, but when you fabricate what is available to you, you have to check in. So I simply type FR4 and you could see FR4 epoxy being selected. If you want to know the property, once again, I'll just right click on this, edit. I'll show the property. You could see the property in this. If you FR4 epoxy, 4.4 relative permittivity, and that's what we are using in our design equations actually. Okay, so we have selected it, and if you want to use some color, you can choose. This will be able to visualize the object actually. Substrate will be any color you want, you can just add. So you double click on this box one, what you have created, and assign a name and choose a material. And then if you want, you can put some color over it. And then you okay. Now you could see that object change to substrate actually. Still the dimension we have not entered. Then click on the create box to enter the dimension. As I said, we are going to start at 0, 0, position. At the origin, I am starting. So I want to keep the surface at 0, z equal to 0. So the dimension x size is nothing but the, I will just look into my worksheet. So substrate position is 0, 0, 0. X size is 68 point. This is what we have calculated. This is the width and length plus lambda by 2, lambda by 4 we have added, right? I hope that's clear. Then the y dimension, x is 68 and y is 62. Just enter this value, 62.828. Look at this. And z size is the thickness. I'll give minus 1.6. We need a thickness of 1.6. Why I give minus 1.6 is that I want to keep the radiating surface at z equal to 0, right? So I'm just drawing the substrate down that z in minus z axis. So the substrate thickness will go down. The top of the substrate will be at z equal to 0, and the bottom of the substrate will be at z equal to minus 1.6. That's the reason I have done that. And we got this value of width and length of the substrate by adding lambda by 4 on the left and right side of the patch and top and bottom of that. That gives the substrate length and width patch. Okay. So I apply this, and you could see once you enter the dimension in this create box under the substrate object, it goes to its position according to the coordinate. It goes and fit itself actually. So you can zoom it, or so now you have created your substrate actually. Okay, right. So the first job is over. We did the substrate, and then let us draw the ground plane. So the PCB, all the microstrip structure will have a copper ground at the bottom actually. So we'll make a copper patch at the bottom. This is not the radiating; it's a ground layer, copper ground layer. So for this, I'm not choosing box. I'm choosing a sheet because the copper thickness will be negligible. So that's the reason why I have chosen a sheet actually. So it doesn't have any thickness actually. So infinitesimally small layer of copper at the bottom that's going to act as the ground layer. So I have chosen a rectangle for the ground layer, right? Okay, once you draw a rectangle, somewhere you can draw in the workspace. Again, you could see an object named sheet here and rectangle 1 because its shape is rectangle. So you can double click on the rectangle here and then give the name. It is ground. If you assign proper name, it will avoid ambiguity and confusion. So the ground layer is a copper layer. This is not material. I'm just assigning some color just for my observation actually. It is not material. In the structure, I could see different color, the ground, and if you assign different colors, you'll be able to visualize it. This is not the material actually. So we have given the name by double clicking on the rectangle, ground. I made it ground, and color I have chosen. If you want to change the transparency also, you can change it. Give okay. So now we have to give the dimension. So what's the dimension of the ground sheet? The ground sheet have 0 thickness, z equal to 0. So its dimension would be same as your substrate actually. Only the position is different. You have to draw it at the bottom. The origin is different. So I expand this ground. I click on create rectangle. Now I have to enter the position. So x position is 0, y position is 0, 0, comma, 0, comma, but z equal to minus 6. Z axis. Position is okay. Position is 0, comma, 0, comma, minus 1.6. So I want the ground plane to be at the bottom of the substrate, right? So now the bottom of the substrate is at minus z equal to minus 1.6. That's the reason why I'm drawing the ground plane right from z equal to minus 1.6. So it will stick to the bottom of the substrate actually. And x size is same as your substrate, right? It should stick to the substrate. So x size is same as that, and y size is also same as the substrate. So it is 62.828 actually. Okay. So now we have finished drawing the ground layer also. You can see it here, but you click on this ground, and there are some tools to rotate. You click on the tool to rotate it, and just you can see it. At the bottom, you have this ground plane actually. Let us see what color we have chosen. We are given this color. It's okay, no problem. You could see if you click on this create rectangle, then you could see that. So at the bottom of the substrate, we have created a layer of copper. That's a sheet, a rectangular sheet, which will act as the ground plane. Okay, is that clear? Right. Okay. It is rectangular only. It's just looking. You can rotate it if you use this tool. Pan tool is used for moving this, and with your mouse you can zoom in or zoom out actually. Okay. Then what's next? Now we have to draw the rectangular patch, right? Okay. So in the PPT, you could see the steps. We are first drawing the substrate and assigning the material, and the next step is entering the dimension. What we have seen, we got the substrate, and then after that, we draw the copper patch behind this. So we choose rectangle, enter the dimension. Okay, after drawing this, when you draw a copper layer, you should assign, for substrate you have assigned it is dielectric material with 4.4 permittivity, but for this ground layer, no, you should assign what material it is. For a sheet, you should tell. So how to assign that? You click on ground, right click on it, then just I'm assigning what material it is. You could see assign boundary. So I'll just simply tell it is perfect. It's a perfect electrical conductor. I'm not telling it is a copper or a aluminum or a gold or layer, whatever it is. Simply I say it is a perfect electric conductor. That's what you can do for all conducting layers. Okay. So the ground layer is a conducting layer, so you can assign perfect. Once you assign that, you could see this. We have assigned that material is a perfect E actually. Okay, right. Then next one is the patch. Right now, the third one is drawing the patch. You could see here this one we should make it right, and we got the dimension of this, and the position, as I said, the substrate should have lambda by 4 gap on all the sides. In the feed direction, it could be greater than that, but right now I have chosen lambda by 4 surrounding all this, right? So with that, I should find out what is the position, where to start drawing this rectangular patch, right? So it should be lambda by 4 away from this x axis and lambda by 4 away from this y axis. So that will be the starting point of this patch. Then from that point, you can give the length and width. You create this structure actually. That's what we do. So there's a little bit of calculation you should know. You know what is the origin, and you know what is the gap from the edge to this. It should be lambda by 4, right? I said lambda by 4 is 21.42. So from that we should, from here, x it is 21.42, y is 21.42. That's the starting point of the patch, and z equal to 0 because the top layer of the substrate lies on z equal to 0. So that's our position. So we start from here, and then the x direction, x length would be the length, and y direction would be the width. Actually, we have to enter that. So that will give us our rectangular patch actually. So I'll go to the software now. So the top layer is also a copper layer. So I'll again use a sheet here, and then I just you get here once again a rectangle. Initially, first change the name. That would be good. So I name this as patch. I give some color for the patch. I'll give some pink color or something. Any color you can give. This is done. The patch is created. Now let's give the dimension for the patch. So position, as I said, x is 21.42. That's a lambda by 4 gap actually. Okay. Then y also 21.42. The gap is there, right? From the patch to the edge of the substrate. Please put comma 21.42 comma 21.42. That's a xy dimension. Then 0. This is the starting position of the patch. I told already. So this point, the starting that this corner point is 21.42. That's lambda by 4 of the 3.5 GHz frequency. That's a gap generally people leave. So in x and y, it is 21.42, and z equal to 0 because this lies on the top of the substrate, right? Okay, it's done. Then x size. Now it is your what is x actually? You can give the dimension of the patch actually. Okay, you could once again look at this. The length of the patch is what? The length of the patch is we are in the so according to that our coordinate that L is y dimension and width is x dimension actually according to our coordinate because we are following a unique xyz coordinate. So now I will go here and enter this value. So this value is already calculated. For the patch, x dimension is 26.082 and L is 19.988. Always W will be slightly greater than L actually. In fact, W by L should be less than 2. That we should see that. Okay. Okay. So this is a length and width we calculated using that EM website Microstrip patch dimension calculator. And Y size, okay, we have given that. Yes, sorry, I had to give separately. I'm sorry. So X is 21.082 and Y is 19.88. 19.8. Sorry, 988. So more precisely you give the values, more resemblance will be the designed and simulated values. So I apply this value and you okay. Now you could see the patch going and sitting in its respective location as with respect to that coordinate, right? So we have finished the patch. So now I'll go with the rectangular feed line, right? Now we have to draw the feed line. Okay. One more thing, for the patch also we have to assign that boundary. It is also a copper layer, right? So assign boundary, you can give perfect E. So it becomes perfect E now. It's a conductor, we are telling it is conductor. Then draw the feed line. Now we have to draw the feed line. I'll show this. Okay, another feed line is a rectangle, right? As I told, I'm going to use that a quarter wave transformer, right? So two different lines will be drawing here. One will be slightly wider and the other line will be shorter because that will give you a better performance. So I'll draw first feed line 1 and its dimension would be, okay. We have calculated that feed line 1 is going to be at the edge of this. So its width, we got it as 2.8, right? Okay, that we are going to draw. Unassigned rectangle. So this is feed line 1, I'll put. So I'll make the same patch color so that it's a same copper patch. I've drawn this. Now we have to enter the dimension for this feed line 1. So position is I'm starting from the edge of the feed line 1, feed line 2. Okay, 32. I already calculated 32.93, comma 0, comma 0. Okay. Okay, so this is the starting point of the feed line, and its width is, it is 2.98, which we calculated using that microstrip line calculator, and y size is the length. I'm not drawing a single rectangular feed for the length 21.42. You can try it actually. You can first try with a single strip of, you can put x y size equal to 21.42. So yes, single strip will go and join with the patch and you can see what's the result. Means time is running short. I'll go with that quarter wave design directly. So 10.71 I've drawn, it's apply. Okay. So I have made one feed here, part of this. So the next line, I'm going to make it more narrower because it's going to be a quarter wavelength transmit. It's a thinner line, that's all. Instead of having uniform width from the edge to the patch, I'm going to use a smaller one that provides better results. I'll show you in the results actually. Okay, this is joined now. And then another feed line we have to draw. So again, we take a rectangular thing. Feed line 1 we have done, it is not assigned, so you can go to assign boundary. This is important because we are telling what material it is. It's a conductor, we should tell, then only the software can analyze exactly. Then rectangular, another rectangle we have drawn. Patch is over, ground is over, feed line 1 is over, so another rectangle we have drawn. I'll make this as feed line 2, feed line 2. So I'll use the same color because all are copper patches. Apply, okay. Then we should give the dimension for this. So the remaining length we are drawing. So starting point is now moved 33.716. It's a position actually 21.420. This is the starting point, and the x dimension is, see now its thickness is less. The previous one is 2.98, and this one I'm reducing the thickness for impedance matching actually. And the y size is minus 10.71. So why y size minus, I'll tell. Okay. So I started this as a starting point actually. So the starting position is here at the meeting point of this feed line 2 and the patch, and then I give the x dimension and then this y dimension. So since we are drawing the reverse direction, the y is negative. If you give y as positive, it will go this side, right? So that's the reason why we made y as minus 10.7, so that that line will come back in the reverse direction. So now we have made the feed, and again you assign this rectangle as a perfect E material. So all have been declared as copper. That's a perfect conducting material. The next thing is we have drawn 3 different objects, right? Even though they are touching one another as per the dimension, they are physically independent now. They are not physically intact according to the software tool actually. So we have to merge them, and after doing that, unite. That's called uniting. We have to unite all the 3 segments, and then only the software will consider as the 3 objects as a single entity actually. We have to join the feed line 1, feed line 2. I have not named it, sorry. I'll once again make it feed line 2. If you name it, actually you can avoid ambiguity. You can easily go to that object which you want to edit, and I think it is not accepting any space in the name, that you should see that. Okay, so easily you can go and edit that particular component if you give the right name actually. So we have drawn it, and we have declared all of them are perfectly, right? That the feed line 1, 2, ground, patch, all are copper patches. Then what you do? Okay. As I said, this still they are independent objects as per the software, so you have to merge them together. For that, they are given the option. You select it, what and all object you convert to a single object, feed line 1, 2, and the patch, right? It's a single layer, just we etched out. So we want to combine these 3, right? So select the elements which you want to join, then right click and you select edit, and then here you could find the boolean. You can add or subtract. If you want to make a slot, we use the subtract option actually. Now we want to join, so select this unite option. So once you do this, now the object has become, you could see there are no boundary lines in this objects. Earlier you could see small boundary lines, but now there is no line. It's a single object now. Okay, right. Okay, our design is over. So we have created the microstrip structure in the software tool, right? It won't be difficult. If you just do 1 or 2 design, it will become very convenient in doing this. Okay, next what's the job is, we have to declare, you see after uniting, you could see all in this. Only if you expand the unite option, you could see. So all this have been combined. That's what it means actually. Whatever changes we make in the geometry, that reflects in this object window actually. Okay, right. The next thing we have to do is port. Someone asked what kind of port you have to. So what is support as far as the geometry we have discussed, we have created our design as per the dimensions. It's over. But for the software point of view, we need to declare the port actually. So port is nothing but I'll just open this and rotate. I'll change the direction here. Port is nothing but I want to just tell the software in which cross-sectional area the software is going to excite our structure. You are going to connect the source, right? So the software should be told in which cross-sectional area the source will be excited into the structure. Once you that is done by defining the port actually. So it is not a part of the geometry. It is required only for the software tool. As for the geometry, the antenna it is over. We have done it, but it is required only for the software actually. So that determines the area in which the field will be applied, the excitation will be applied into the structure, and then it will analyze the radiation pattern and other parameters as well. Okay, so to do this, just we have to tell the area. We have to draw a rectangle. That's a cross-sectional area in which the feed signal will be applied into the structure. So simply we are going to draw a rectangular sheet, nothing else. But this time here we have to draw in this covering this from the ground to top. We have to draw just next to that structure actually. So since we are going to draw a rectangular sheet, I change in the ZX plane actually, right? It's going to be vertical, right? Now it is flat. The sheet, this sheet is flat. The patch and all it is flat in the XY plane, and this rectangle is going to lie on the edge of the substrate, right? So its axis is different, right? So I change this to ZX axis, right? Now you can draw this. As you look at it, I'm just drawing a simple rectangle actually. Anywhere you could draw, no problem. I'll give the right dimension. Now you created another, I think this is port actually. So it is not a part of the structure, it's just for the software. I just name it port and I give some other color. Okay, then apply. Okay, this is just a rectangle we have drawn, and then we've named it as port, and let us give the dimension. So it should exactly lie between the top and bottom of the substrate, right? So we have to give the right dimension. So the position of the port is X, draw rectangle. Okay, so the port position is X is 32.93 and 0, 0. We start at the top edge of that feed line. Just we start here actually. Here we are starting. This is a position I'm entering here. 32.93, 0x is 0 here. Sorry, x is 32.93, y is 0, and z is also 0. It is on that plane. And then y axis we are drawing. The x size is that the height actually. We know the substrate height is 1.6, so you can straight away. Sorry, z is the height. It is 1.6 minus 1.6. It should draw in the reverse direction. And the x size is that this is width of your feed line. It is 2.98 what we are saying. So just I'm giving the dimension for this. It's this is a starting point position, and x size is this width. This width is 2.98 at feed line width, and this height is 1.6, right? So minus 1.6, it is going down, right? From here it is going down, right? So it is minus 1.6. We got the structure. Now it exactly fits here. You can zoom and check if there is any air gap between this port and your structure. You'll get error actually. It should lie or it should touch that. It should not go inside the patch dimension. It should just lie in the boundary exactly, right? Okay. So now this is the area where the feed signal will be applied to us. It can be larger than this also, no problem in that. You can keep it larger than your structure. You will get a better performance. But for professional analysis, we'll keep the say exact dimension at the edge actually. Okay, that is done. Now we have to tell what it is. This is not a copper conducting layer, right? This is a port, right? So we have to declare this rectangle is a port. We should tell that. So I'll select this port and right click. And now you could see I'm not selecting boundary, I'm selecting excitation because it is the port, the area in which the signal will be applied. So somebody asked why a lumped and wave port, and lump port is normally used for microstrip design. So that input impedance, I'm telling 50. It means the source excitation impedance would be 50 ohms. Actually, that's what we are telling here. And then it will ask for integration line. The integration line is nothing but the direction. I just select here a new line. And it will be none here. You just click on that and then select new line, and you'll get an option to draw a line. This line tells the direction of the electric field. That's all, nothing else. So the source is going to apply energy into that, right? So what should be the direction? The electric field should always see from the bottom to the top, right? So we are defining the direction of the electric field of the source excitation. That's done by drawing this integration line actually. Okay. So that's all. Once you draw this port impedance becomes 50. This impedance is 50. Here the impedance is 50, no problem. This feed line also around 75, 50, no problem. But when it comes to the patch has a different impedance. So you'll get mismatch. And that's the reason why we have reduced this dimension. This length is called a quarter wave. And it is not, now I have not exactly used a lambda by 4 length actually. Just I want to demonstrate that concept. And this will do the impedance matching between this 50 ohms and this 290 ohms patch actually. Okay, so all our job is done. We have designed the structure, we have created that port, and we have assigned the port also. You should check whether the port is assigned or not. It should be a lump port or wave port. Even if you click wave port, it will work actually, but we generally keep a lump port for this patch antenna. Okay, right. Our job is done. Then one more small step I'll give here. So HFSS wants us to create a air box surrounding the structure actually. So this structure should be kept inside a air box. So we have to create a air box surrounding that covers this entire box. In the previous versions, we have to draw that, but now the software automatically creates that. Right? What we have to do is simply go to HFSS, or you can simply right click here, and you could see this create open region, and it will create a box. Operating frequency, this is just the radiation boundary. So what is the boundary at which the software has to evaluate the radiation field values? So that we are defining. And it's a air box surrounding the structure, nothing else. And it lasts for, I'll tell once again, you just right click on this window. You could see create open region, and then it will ask for the operating frequency. The center frequency of our design is 3.5 gigahertz, and boundary radiation you give, and then you okay. So automatically you'll get a air box actually. So with this you will get a more accurate result actually. If it is not there, also you'll get results, but there could be some mismatch actually. So we have designed it. Our job is done, right? So now we can cross-check whether our design has any bugs or errors. We do compile and check for errors, right? So similarly, we can do here in this software, there is an option. Here you go to select HFSS and validation check. You click on that, it will show. So design settings is good. 3D model is right. Boundaries, excitations are clear. Optometrics, radiation, all things are done correctly except analysis. So we have not yet set the analysis. So what frequency it should analyze, what's the frequency range it should do, that we have to set actually. So once the design is done, you could see various things here. To set that analysis, right, you come here in the project manager window. Once again, your design is done, that's over. You come to this analysis and just right click on this. You'll get add solution setup. So for what frequency the software should analyze actually. So that's called solution setup. We can tell what center frequency, what's the range, all this we can give in this. So you once again I repeat this analysis, right click on this, add solution setup, you'll get it. It's called setup 1 actually. So frequency, this frequency should be the center frequency of your design. So our design is for single frequency, right? So we can give 3.5 gigahertz, maximum number of passes, you can give 10. Delta step size actually is 0.02. This related to that FEM solver actually, this inputs. This is standard values you can keep, but frequency depends upon your design. Okay, done. This is done here. Then you give okay. So this is done. Okay, then once again we click on this analysis. you'll get another option now, setup. You double click on that. Here you have to give the you right click on that. You'll get add frequency sweep. So setup we have created, and then right click the setup. You will see the option add frequency sweep. Here we tell about the range, actually 1 to 5 GHz. I am interested in 1 to 5. I want to analyze antenna from 1 GHz to 5. You can give 20 GHz or 10, up to you, up to your requirement, right? And then just give OK here. That's all. So we have set, once again you go to validation check and see that you have done all thing. Now analysis setup is also done. We have told what frequency the software should analyze, what's the range it has to analyze. All this done now. Now we have to run the software, right? So we have to tell the software do all the analysis. So go to HFSS, click on analyze all. Okay. So I'll save this as project 3 web some. Okay. I've saved my design and it is going to analyze. So when the software is it will take some time depending on the computing capability of your machine. It could be 5 minutes, 10 minutes, or even 20 minutes, half an hour. Memory and all that decides how much time it takes. Now it will be over within 10 minutes. Till then, I'll just show you in the presentation what I'll just recollect what we have done. We arrived at the specification from the starting point. Then we created the substrate, and we then made the ground layer. We entered the dimension for the ground layer. Then we made the patch, and then in the first design, I have just put a single feed line of same uniform width, actually 2.98 what we have designed. And you could see what is the other things are same. We have declared all the copper patches as perfect E. We have edited that. We declared the port, and then we created the port. We created the add box, and then we did the analysis. Okay, sweep, everything is done. And after analysis, you could see the result. Actually, we have designed the antenna for 3.5, but this antenna has a higher return loss as -5. So the antenna should have minimum -10 dB of return loss. Then only we can say the antenna operates at that frequency. Instead, the operation goes at a higher frequency, right? So it's not, it's working actually. It's -5, but it's not perfectly working, you could say. It's not practically acceptable. It should come down to -10 dB. This happens because of the impedance mismatch, because you have taken a straight feed line, right? You have taken a feed line of uniform width, and due to that, there was a mismatch between the patch and this feed. So you had a difference in the performance. So one thing we can do is we change the patch dimension to bring this resonance to 3.5, or you can work on the matching technique, right? So to avoid this only, we have done that reduction in feed line width, actually, so that you could see how the result would be. And this is the radiation. The radiation pattern was fine. Ideal pattern of a patch, and now we got with the straight line feed, but only thing is the return loss at the frequency of interest, actually. Okay, so I think it's run. Okay, so once simulation is over, you could see normal completion of simulation on server. So without any errors, the frequency sweep has converged, actually, right? So now we could see the results. Okay, I'll go to HFSS. How to see the result is HFSS fields, results. You can go straight away. Then create model solution data report, rectangular plot. This is to see the return loss. That's S parameter. S11 is nothing but the return loss, the ratio of the input reflected power to the input power at the desired port, and we'll get it. Okay, new report. I'll give this. I'll close. Now you could see with the straight uniform width, it has somewhere around 5. But now with that, it comes around 3.5 or desired frequency range. You can further optimize this slightly. Actually, I have taken some approximate calculation that even up to 3 digit, if you take after the decimal point, if you could take up to 3 digit for all the calculation, then exactly we can get it. That's not a problem. We can slightly, as I told, what's the main reason for this small drift is that that feed line area, no, it is not exactly lambda by 4, because lambda by 4 itself is 21.42 but I have taken the total length of the feed as 21 point. So if I work on that, I easily make it 3.5 actually. So always we do some small optimization to bring it to the desired thing actually. By either two options you have, you change the feed line, or you work on the small changes in the path, patch width or length you can vary and bring it exactly to 3.5 GHz. Okay. And then radiation pattern also you could see. So as per our design, the antenna works well. And if you want to see the radiation pattern, one thing you should do, you go to radiation inset far field infinite sphere, and you can make it 0 to 360 in this. This radiation pattern, engineer Vinod will explain well further analysis. It's done. Once again, I'll just give analyze all to see the radiation pattern. Okay, it's over. It is now analyzing the radiation patterns. I'll go to radiation results. I'll go once again. Far field report, 3D polar plot. I want to see the gain of the antenna. In dB, I want to see. Okay. Okay. So I want to plot the gain in decibels. You get a new report, and you could see the ideal radiation pattern. And here you could see the gain of the maximum gain of the antenna is 3.7 dBi actually. So from this, if the gain is positive, the antenna is well and good and suitable for applications actually. Okay, right. So we have made the design, and the simulation almost comes close to it. A little bit of optimization can bring it exactly to 3.5. And next factor, if you want to increase the bandwidth, you can try on changing the substrate material with different dielectric constant, and you can work on some changes in the patch shape to acquire the desired bandwidth actually. Okay. And further analysis and optimization of this same design will be done by Mr. Vinod actually. I'll hand over the session to engineer Vinod to further demonstrate the analysis of this proposed design actually. So as you have seen, once you know these basic steps, you can design for any frequency, any shape you can draw, because you have the different shapes, library packages. You can simply select the shape you want and you can make it. You have option to etch away metal patches, so you can introduce slots. Anything can be done with this 3D tool actually. So it's just a matter of proficiency in the tool to design antennas in a fast pace actually. Okay. I hope this demo will be useful. And any queries you have, you can ask. I'll hand over the session to Mr. Vinod. Sir, Vinod sir, are you online?
Yes, sir. I'm on.
Sir?
Thank you, sir.
You have the design
Hello.
file, right? You have the design file, right?
No, sir. I'll just explain in a theoretical manner. No problem.
Okay, sir. Okay. Thank you.
Yeah. Okay. And good afternoon to all. Sorry, good morning to all. Myself, I'm a Vinod Manoharan. I'm a founder and then head of the Pelma Communications groups for an Asia, US, and then Europe continent guys. Okay. Our leading product is an antenna manufacturing, and also satellite design is our main import factors. Now we have the session is very useful for us, I think, maybe because Sir having more than 20 years of experience in that field. Also, he is an doctorate holder in the same field, and also he is working as an external research advisory people. Okay, let me come to the point. Today the topic is a 5G related modem antenna design prospects. Okay, here, so before enter into the design parts and then design classifications, and before having some basic knowledge of 5G, I told the basic knowledge of 5Gs. Okay. Here in before that we hear about a lot of technologies, right? 1G, 2G, 3G, and 4G, or 4.5G, and 5G is that. So 5G is the recent implemented technology. It's not a completed one, and still now. And before that, the 2G. 2G means it's like only have the text queue formations. It's not an internet connectivity for us. It's just a text format. So next we have to move and around the functions. That means increase the duty cycle of the function. We get some wide bandwidth. So on the wide band spectrum, we got some advantaged things. The advantaged things means we get internet facilities in a phone. That the technology is called as a 3G. That means edge network. Edge and edge plus network is that. And next move on to the 4G means we have to get a video call functions. That means a video streaming function is there. In that video streaming functions, we get some non-quality video function is there in before 4G. And then after that, the LTE will come, the 4.5G, we get some HD qualities and at all. So these are the generation formation of the telecommunication networks. And a 5G, we got a same progress with complete automation of the HD qualities in that things, because the bandwidth is wide enlarged, and also it's working more enumerable functions. So that in a 5G have to use a Shannon capacity theorem. I think you all know about the Shannon capacity theorem. So to increase the capacity means we have to merge the power. We have to we have to consider a low power with high node applications. In the high node applications means nodes, each nodes having a very less power consumes. Then only we achieve the capacity, more capacities. So that is called a success rate of the telecommunication network. As a compared to 2G to 2G to 3G, its a success rate is around 48% is at a success rate. So 2G to 3G, and 3G to 4G, the success rate is around a 62% for the high enumeral functions. And next is the 4.5G, the LTE functions having the implementations of 71%, because we getting a streaming downloads. If a streaming download means we can't get a flat trap of download speed, but the speed will be a varied one, but an achievable one. That is the condition for an enumeral function. And next thing is a 5G. So 5G is more important and then sensitive cases also, because the 5G frequency is a very large frequencies and also getting a more power enumerated frequencies. So that we have to calculate a lot of things. So the first thing is a new cellular architecture. We frame a new cellular architecture, and then we improve the capacity functions. Those are all the important things. And then next thing, the 5G. Why we called the technologies in a 5G? Is there any idea about that things? It's nothing but the 5 technologies implemented in the single network is called a 5G. What are the 5 technology means? The first one is millimeter waves. So all know about the millimeter waves. It's a 30 gigahertz to up to 300 gigahertz. This range is called as a millimeter wave range. And also we have a sub 6 gigahertz millimeter waves. That range is around 3.4 to 3.6 gigahertz. I think sir designed at the same frequency, 3.4 to 3.6 gigahertz frequency. This is called a sub 6 frequencies. Okay, and the next thing is a small cells. I don't know, you all hear about that things, but in a future, that means after 2022, you want to see the mobile phone towers, because we are using a small cell towers. The small cell tower means it's not like a very big tower and at all. It's like just a 52 centimeter cross 42 centimeter, one small box itself. Each and every home having a own individual network accessibility box. That box is called as a small cell. That small cell is having a lot of variations, femto cells, macro cells, micro cells, and then that means next MSM technologies is there. So that is things is called as a small cells. And the third one is MO, so multiple input and multiple output concepts, because at present we have a multitasking function, right? Now we have to see in this video in a one part, and another splitting. We have to use the splitting window means in another one webinar, or else whatever it's going on another thing means that also you have to see. So this is called as a multitasking functions, and that multitasking function is occurred in a same network. That is called as an MIMO technologies. And next one is a beamforming technologies. The beamforming means you have to form a beam in the particular application in a particular directions. For a multi-beam, you have to generate a multi-beam in a FTP concepts. that we get a lot of versions. That means each and every application is in a separate beam, and that separate beam operating on a single frequency. That means bandwidth is classified into the multiple channels. We get a multiple outputs. That is the main concept. And next, the final one thing is in a full duplex method. So in each and every network, in before that, and 2G, 3G, 4G are having working as a half duplex mode. But in a 5G based things, and 5G and above the network things are working as a full duplex mode. So these 5 technologies inbuilt into the single network is called as a 5G. That is the most important things. And then next one is small cell. At present, if you are in a Bangalore city, means you all know about the small cell concepts, because each and every home having one small box is there. That means a white color paletted box, whether it's a rectangle or a square taste shape, whatever it's, that box is there. That box is called as a femtocell. Each and every home having that femtocell values. That femtocells covers, it's an indoor application. That means if in your home itself, it's working as a base station antenna. Base station, okay. So it's a power range is a 10 milliwatt alone, and then that range is 10 meter. That means 10 meter only it covers. It's no more than 10 minutes, it's not working. And then move on to the next thing is in a picocell. The picocell is around above 100 meter, and then macrocell also above 150 meters, and then microcells is above 150 meters, and macrocells is cover a kilometer radius area. So one macrocells is enough to cover an entire town. So single unit, so it's cover the entire town. Entire town means around a 3.5 kilometers, it's cover a single unit. The unit cost is just 5,000 rupees alone. That the power level also very low, below 10 watts alone. But if you take on a one mobile phone tower, means it's having a 3 sector antennas, that is alpha, beta, gamma, 3 sectorial antennas, and then each antenna having the power range of 2.5 kilowatt. So 3 means it's getting around a 40 kilowatt. If you want a 40 kilowatt function means, then only it's operate, but it's cover around 500 meter alone. But in a macro cell, it's very low level, low power level, but it covers a kilometer radius. That is called the advanced technologies in a 5G mode factors. In a Bangalore city, if you take an electronic city, means in a Bangalore electronic city, you take an electronic city means it's the best example for the microcells division, because in that electronic cities, mobile phone towers are band 1. So they are all using picocells and femtocells alone. So these are the advanced technologies you have to work in that field. And then next thing, the next thing is come to a design point of view. In the design point of view, sir designed on a basic antenna. Sir designed in a femtocell antenna, and that femtocell antenna is working as a 3.4 gigahertz. In that bandwidth is around, it comes around 200 megahertz alone. Because this femtocell, this femtocell and picocells are the very low bandwidth cases alone, because the bandwidth is very narrower, means it's getting a high valid application. That means if you give a power of 10 millivolt, means the entire power will be operating in the resonant mode. That means it's evaporated in the radiation manner. That three-dimensional structure will called as a radiation pattern. I think those are all done in one lab, right? In your, I think, I don't know exactly that lab name. In that lab, you have to function at one antenna. You have to place one antenna is in a reference antenna, in another one antenna is in a testing antenna. The testing antenna is placed in some rotating board. You have to take values in that particular angle rotation mode, means you're getting the waveform of around in a 8-shape waveform. In that 8-shape waveform means it's in a bidirectional antenna. That means the 360 degree it covers, means it's called as a bidirectional antenna. Then above 360 degree, above 180 degree means it's called a unidirectional antenna. But in most of cases, having if you go for a microstrip patch antenna, means that antenna should work on around the antenna should work in a bidirectional mode alone. It's not a unidirectional pattern, because it's a low power consumes and also working as a high speed transmission with a large distance coverage area. That is the main scope of that microstrip patch antenna. That's why in a 5G network, all the elements will all the antennas will structured in the manner of microstrip patch antenna. In before thing means through 3G and 4G means you saw one box, that means a rectangular box in that mobile phone tower. In that rectangular box, it's having a dipole antenna in a serious manner. That means array mode. The dipole antenna will covered in the unidirectional region. That is called as a mobile phone tower antennas. That antenna is called as a friction antennas. But in a microstrip patch antenna means it covers a entire 360-degree. That's why in that mobile phone tower having one drum shape antenna is there, and the drum shape antenna is focused on only the one direction, but it covers entire 360-degree. So that is the main impact factor for a microstrip. That means a microwave antenna design. Hope that radiation pattern means the two condition is there. So one is a near field is always zero. So antenna near field is an always zero, and then far field only we getting an output. The maximum power delivered in the mode of far field alone. In a near field, it's in a zero mode. That means a zero mode means the load will act as in a direct manner. So the electrical loss will dissipate in that same process. So that radiation will not occur in that mode. That's why we say the near field of the antenna is a zero. That formula is 2d squared divided by a lambda. We have to use that formula means we find out the near field pattern and then far field radiation pattern things. Okay. So these are the basic things, and then basic analysis of that microstrip patch antenna design. For here today we have to see about the 5G modem antenna design. In that 5G modem, we have to use a two set of frequencies. One is in a 3.4 to 3.6 gigahertz, and another one is in a 5.1 to 5.25 gigahertz. These two things are used in a 5G modem, but still this modem is not in not in the market availability under in a research progress alone. We find out we have to frame 5.2 gigahertz 5G modem. We'll show in our next classes, and then. Okay, if you have any doubt means so please ask, because I think all the information we'll have to share. So if you ask a doubt means we'll clear on the doubts. Is there any doubts? Because continuous section will getting a very bore. That's why I'm asking a question back. If you ask us some question means I'll explain that question related in a wide manner. Is there any questions?